Okay, so 4, 7 plus 4, 11, 12. Okay, so some more students who were supposed to come didn't come, but so this is 576. I hope everybody is for the same class. I see some people have taken my course. Who's not taken my 575? And you took somebody else's 575? Munte. Yeah, okay. And you also? Did you simultaneously register for both? Okay. Anyway, and you took 575 some time ago. Okay. Uh, anyway, so welcome to this course. As you guys know, so some of you haven't met me. My name is Teja, and I'm an assistant professor in the Department of IDS. And so I generally teach both the statistical models and methods and advanced predictive models. So the informal name for the first course, the 575, is basically machine learning core. So because we go through the basics of machine learning, and this course, the informal name is actually it's an elective. First of all, you chose to take this course, and the informal name is basically deep learning, graphical models, and reinforcement learning. So these are three, I guess, full-fledged areas in themselves. But we will pick the most popular things among them and make sense of them, make sense out of them. Okay. So I think this will be, so I'll have a very quick course logistics overview. So this is an elective course. Most of the communication will be through the forum. I think some of you already have accounts from previous semesters. So those who have not, sign up with the forum. I think so. You've taken my courses, right? Yeah. So they know. So this is the forum page, and I've actually from previous semesters I've copied some questions which are useful for our semester as well. But we can continue our discussion, and they will come out as new threads at the top. Okay, and so we'll discuss this first thread pretty soon. So other than that, as you know, the context is basically this complements or extends beyond the techniques that you've seen in 575. So typically in 575 or the machine learning basics course, you kind of work with tabular data and did a little bit of feature engineering as well in your assignments or your projects, um, and saw how, what's the difference between just using k nearest neighbors versus linear models versus things in between like SVMs or random forests or gradient boosting techniques, right? So here the emphasis is on like increasing your toolkit to situations where you have unstructured data. So one of the biggest unstructured data which everybody kind of tends to work on at least at some point of time in their life is text data. So maybe it's reviews or comments in surveys, things of that nature, and even data from websites and so on. So text data is inherently unstructured, so you want to make sense out of it. And in fact, there are full-fledged courses, natural language processing for them. But we'll see that whether it's text or images or videos or audio, they have some structure in them which can be exploited using neural networks, in a very parsimonious manner. Okay. Um, so I'll quickly discuss the learning goals. Actually, there are a few experimental videos from previous semesters. So if you want to have a look at those videos, um, logistics as basically there's going to be optional recitations. At the location is not known, but it's on Wednesdays. So we have TA Daniel. Some of you probably have met him, and my office hours are on Thursday from 2 to 3, and TA's office hours are on Wednesdays and Tuesdays. Okay. Um, Let me get to learning goals. But before that, some other simple logistics. So there are three reference books actually in this course, one for each subject area, one for deep learning, one for reinforcement learning, and one for graphical models. Okay, so all these three textbooks are freely available. So have a look at them, at least the introductory chapters. The software for this course is going to be Python focused. So how many of you have already a good knowledge of Python? I see some people. Yeah, some of you don't. Worked on Python before, but then yeah, I don't have good knowledge. That's a good point. So you were supposed to infer what good knowledge was and then tell me, but that's okay. So Python and basically you can use Jupyter, or if you like to work on with IDEs or directly with Python files, and that's fine. Um, and Okay, so before we get into lectures, uh, there are four assignments. Typically, you will submit using a notebook file. Okay. So for the first assignment, I've already created a notebook that you can download and work with. The assignments will involve some neural networks typically, and you can actually. So that comes to the point of you can actually use some GPU machines that I have commissioned for this course. So we have few machines, and since there are not too many people here, so you can solve the assignments in groups of two, okay, uh, or groups of three if you want. Okay, if you want to distribute load. There's also a project component for this course. There's details provided in that link. Have a look at it and see when the deadline is. It's pretty close to the end of the semester. Okay, so these are the deliverables, and there are two exams. Exams are not asking about coding. Okay, nothing about Python, but mostly just conceptual understanding of some nuances with the deep networks that you will see, or nuances with reinforcement learning, or whatever it is. Yeah. Okay, the subject. Um, and so this is the split up of the grades. Okay. So, any questions about this very quick course logistics? So it's mostly lecture format. I mean, the assignments will be very hands-on. So hopefully, and they'll be aligned with what the lectures are going to be talking about. Okay. So any questions about this? No questions? Yeah. Is it the entire portion or only the? So we will cover only the second part. Yeah. I mean, exam one is already tested on the first part, so I'm not going to test again. Um, okay, so let me. Um, so as I said, there are a few machines available, right? So assignment zero, which you should open this forum and sign up if you're not on the forum. But assignment zero is essentially creating some, following some simple directions. First thing is these machines. They are basically Linux machines. Okay, so you need to send me up, what are called SSH public keys. Okay, so just look at these links to figure out how to generate a key. Okay. Um, I mean, you should also try to experiment working with GitHub and Git in general, but figure out how to generate a public key. It'll actually create two files. Okay, when you run those, there are a couple of commands. In fact, one command I think you need to run. It will generate a couple of files. The .pub is the public key that you can upload it on this form. Okay, I will need it so that I can create accounts for you. And the faster you send it to me, the faster I can create accounts for you. Okay, and you can use so the key is just for you to log in into the machines in a secure manner without the hassle of passwords and stuff. To log in, you also need to be on the VPN and all that. So I will send you a detailed email once you send me the. So if you do this step, okay, I'll send you a detailed email of how to get set up with the machine that I'll assign it to you, and how to launch Jupyter, how to work with Jupyter. Okay. Yeah.
I'm sorry if I missed this, but are we doing assignments in groups?
Yeah, groups of 2 or 3. Yeah. No more than 3 for sure. 2 would be ideal. Yeah. Including the projects. Yeah.
What about the project that is due in final?
That's due before. Yes, that's due before the finals. I mean, you can start working on the project. You can, of course, submit it next week if you marathon through it. Uh, but yeah, I mean, the due date is
It's a group project or
same assignment groups. So don't try to change groups. It's a small, class. So hopefully everybody is enthusiastic and want to learn about these topics. So form some groups. It's just to even out the load. Okay, so I think one person, it may take too much effort. So you want to have somebody to brainstorm and learn. Okay.
One more thing, these GPUs are NVIDIA or
Yeah, they are NVIDIA 1080 consumer GPUs. Yeah, they're a little bit older generation, but they do. I mean, I think their RAM is about maybe 8 gigs or 10 gigs. I don't remember. Okay, so you can do a few of the tasks. You may not be able to do very complicated things. Yeah. So that's that. So let me. Um, so before I think I'll start. I think I'll go over a few. So today's lecture is going to be a little bit lightweight. I mean, the heaviest thing you'll see is probably backdrop, but so let me just discuss the logistics. Sorry, the learning goals. So just like in 575, the goal here is again, like at least modern machine learning or in general statistics is all about you just have data, you want to infer something about the probability distribution that generated the data, right? Typically, that's how probability statistics and are related to each other. Okay, so here the goal of the course is to have a good intuition about various deep learning models or the what I call basic building blocks that have been developed over the past decade. Okay, and then if you understand the basic building blocks, for example, what is the convolution layer, then you can use the layer in 100 different locations. Okay, it's just a function which goes from some input to some output. Okay, so that's what a layer will be. And so these building blocks are just functions, and so you can kind of be confident while using them in different setups and different architectures and so on, and also be aware of some choices being made in this analytics workflow. So in 575 or in for example, if you're running a support vector machine classifier, then you would be mostly concerned about what is it feature engineering, and then there are very few choices you make subsequently, right? It's just maybe the weight on the regularization or the um, uh, slack variables, the constant in front of it. But here there are going to be few other choices that you'll make. So be cognizant of what choices you're making, and in fact, why convolution? Convolution is an operation from, I guess, signal processing, and why convolution makes sense for image type of data. Okay, so you want to kind of have that intuition, and maybe even if you don't have image type of data, can I use a convolution layer, and will it give me any bang per buck in whatever machine learning task I'm doing? Okay, and actually it was Python is the supporting, I guess, software. So sorry, language we're going to use. So hopefully, since you've done R, so you know data frames. So in Python also you have pandas data frame object, and you also have a few nice libraries. You also can interface with GPUs, which seems to be kind of necessary for training these large models. Okay, these models are not easy to fit on regular CPU-based machines. So hopefully you'll be more confident in doing that. And actually, I think last semester, for example, the students who took this course really, some of them for sure, gave me feedback that it was useful for their internships. Okay, during the internships. So maybe it'll be useful for you as well. Okay, so as I said, the goal of the assignments is to get to speed on Python. If you don't know Python, or if you're just a beginner, that's fine. You actually don't need to be an expert in software. And the goal of lectures is to ask, several key questions like why are we doing this, why are we doing that, why can't we do something else? Okay. Um, and of course, make use of the teaching staff office hours recitations. Now we're gonna start with lecture one. Any questions before that? Okay. So this, let's keep it interactive, otherwise people will fall asleep. You guys will fall asleep. Okay, so what's the goal of lecture one? We want to understand. So for lecture one, half of it is just review. Okay, so we will just look at what are the major components in the classification task. Okay, and in fact, some of you probably will just tell me immediately. It's basically data. What's the model class? And what's the loss function or objective function? And what's the optimization procedure? Okay, so basically four things. Second aspect, and I think we'll probably kind of not spend too much time there because all of you already, I think, as the year is progressing from one semester to the other, people are are increasingly already aware of the motivation for why do we need analytics in workplaces. So that's two. Number three is understand how chain rule works. So it's just a refresher on what chain rule is and how it's related to backprop. I mean, that's what backprop is essentially. And and we'll actually revisit. So I don't know. At least in my version of 575, I use a slightly different notation for multi-class. Or just logistic regression because I was um, um, I mean, slightly different notation was used because of the different textbook. So I look at again multi-class logistic regression. Okay, so multi-class just means I have more than two classes. Okay, it's not just binary logistic regression, and in fact we'll just call it a linear classifier. Okay, it was a linear model, right? Remember from from the previous lecture, previous class, logistic regression was just linear model. So for us, that will be like the shallowest, smallest example of a deep network because there is nothing deep there. There is nothing, it's just a simple linear classifier. Okay, for us. So and we'll see why, we'll see an example of it failing, and hopefully in the next lecture we'll see how you can use neural networks to do better. Okay. Um, So I went through the course logistics and the introduction to the course. Okay, there's a few more points. Uh, okay, so I'm actually going to not spend too much time on this slide, but this slide is actually the $1 million slide in any analytics course. Okay, or at least some of the analytics course which teach methods. Okay, so I was teaching methods in the 575 course, and I'm also going to teach methods in this course. But the hope is that your takeaway is to understand the modeling and the nuances required when you pick up any data set. But the reality is that the methods are not the most important part for the success of a product or an analytics solution. Okay, there are a lot of a lot of other things which actually are very important for the success of using data to make decisions or improve something. Okay, and it all starts with what's your business goal. Okay, so you have to have a very distilled notion of what is the thing that you want to achieve using some data or measurements or surveys that you have done. And maybe from that data, you want to create a solution, a product, or a service. You'll probably necessarily have to interact with software engineers, figure out the architecture, and also figure out lot of auxiliary things which are subject of their own courses and topics, uh, and then the last 2% or 5% is the thing with techniques. Okay, so even if the technique is really good, if the data is biased or data is not cleaned well, or your delivery stack has some data leak, the way you're measuring is incorrect, or there's corrupted data, then everything is kind of the technique is itself is useless. Okay, so so that's kind of a very important slide. Big disclaimer, actually. And given that if we can do all these things, maybe the rest of the team or your team can get all these things correct and has experience with that, then you can experiment with techniques to now add more value via modeling. Okay. Uh, so in terms of techniques, the ones in black are something that you've already seen: decision trees, linear classifiers, logic regression, naive Bayes, SVM, even random forests, graded boosted machines. Um, you've already seen clustering, market basket analysis. These are actually really good workhorses, and in fact, they'll get you with these as the modeling parts. You may already be able to model things really well. So even without deep learning, you could have done computer vision. Okay, even without deep learning, you could also do a natural language processing, as in process text data. Okay, you'll get some accuracies of whatever it is. But to if everything else is good, then you can replace that an SVM classifier or some topic model with or a recommendation engine which was based on, let's say, collaborative filtering, to something which includes deep learning. Okay, if everything else works well. So the ones in on in purple are the ones we're going to look at in this course. So neural networks, um, graphical models, and I'll tell you why. I'll spend a few minutes on each one, at least giving you some applications where it's useful, and then reinforcement learning. So let me jump directly into them. So let me skip these examples because yeah. So there were a couple of examples. You should look at them in your leisure just to get further motivated. Okay, so I assume everybody is agrees that analytics or learning these tools is useful in some applications at least because you're already using when you uh, uh, like some of you are using Siri or Alexa or tools like Translate or real time or automatic captioning and so on. So there are already products which are influencing your life. So um, so let's break down the three topics: deep learning, reinforcement learning, and graphical models into what they address, what problem they address. Okay, so when you have structured data, like the usual data they've seen before, like medical data or even advertising data, things where you make measurements at different time, different of different things and different time points or whatever it is. For such data, we've already seen some methods. Okay, mostly we can feature engineer, but we'll see another framework of thinking about this type of data, which is through the graphical modeling framework. Okay, so it's just a way of thinking about the data that you already have. Okay, this tabular data, where each column will now correspond to a random variable. Okay, so which was the case before as well when we were saying x is a feature vector, then each coordinate is a random variable. But now, what we can do is actually, so if it's a random variable, there's going to be joint distribution on it, right, related to it. So this notion of a graph or a graphical model is to talk about this joint distribution over this random variable, input feature random variable, as well as a graph, okay, over nodes which are coordinates of this random vector, okay, such that that graph will encode prior knowledge in a very natural way. Okay? So if you have prior knowledge about this random variable or some measurements like pressure only influences temperature and temperature doesn't influence pressure, then such a knowledge can be encoded in the graph, okay, with some directional arrows. Okay, so it's just a graph of these nodes of the random, coordinates of this random vector, feature vector. Okay, so that's what, in a very two sentence view of what graphical model is. Um, so we'll see how it's relevant. So that's for graphical models. The second part is unstructured data. So that's the data that I was talking about. That's more and more companies are interested in, especially text data. Okay, which is paragraphs, reviews, tweets, social media data, and so on. Or even images, right? Security images, or images from healthcare applications. And even social media images and so on, or even audio and video. Okay, so all that type of data. If you want to glean anything, even if let's say you're a marketer, if you want to look at your own YouTube channel or other related, your industry's YouTube channel, and like get the videos, sample, and figure out like what's the theme of these videos and so on in an automated way. Maybe you can't do a lot of feature engineering. At least deep learning based techniques will already bake in some assumptions about the data and therefore will do some automatic feature engineering for you. Okay, so you will have a less headache with feature engineering with unstructured data if you can use some of the deep learning techniques that you'll see. Okay. Third part is decisions. So typically, at least in 575, we saw a lot of forecasting or a lot of prediction models. Now we're going to look at how do prediction models get tied to decisions that you make. Okay, in the sense that you may forecast tomorrow it's going to rain, so maybe you take a decision that you're going to stock umbrellas in your store. Okay, uh, but then you can so you that's just forward like use of forecasts to make decisions, but then you can also evaluate what happened with your decision. Maybe you stock too much or maybe you stock too less. Okay, so that you'll realize tomorrow, and based on that you will update your or maybe it rained or did not rain. Okay, based on that you'll update your forecasting model in a for loop and then again take decisions and so on. Okay, so there's a for loop of you're getting new data, you're ingesting new data, updating your models. Based on the models, you're making some decisions, and then again repeating the whole thing. Okay, the repeating the whole thing adds some new perspective to this setting, because when you're repeating again and again, taking inventory decisions or taking decisions about what to invest in stock, you may have not just a myopic objective of taking a decision to maximize my revenue for tomorrow, but maybe you care about maximizing revenue for the whole year or maybe the whole decade. Okay, so you will have a issue of being short term versus long term. Okay, not just I mean a good example is stock market, right? You don't want to just maximize the money for tomorrow. Maybe you care about the overall health of the portfolio over a period of time. So things like that. Okay.
So doesn't it happen in deep learning as well in backpropagation? It feeds data internally from its output.
So that's the training procedure. We are talking about let's say some box, okay, whether it's deep learning or SVM or doesn't matter. It takes some inputs and perceives what's there in the input, right? When you think of classification or regression, it's just figuring out, it's solving an essentially a perception problem. Okay, for example, if it's an image, there's a car there, or there's no car. Okay, ultimately that's what it'll eventually do. But given that information, what decisions you need to take is part of like optimization or decision making. Okay, that's a different, I guess, object. Okay, we'll see. Um, yeah. So basically, data variety, structured, unstructured. That's one theme, and the second theme is decision making in sequences. So some of you have seen some of you have heard of what is called A/B testing, right? So A/B testing would be some sort of a decision making where you're just trying out option A versus option B, C, D, figure out that option A is good, move forward. Maybe you will create new features. Maybe then again you test for option A, the selected option versus some other new options. Okay, so that's an example inside this, but this is more, I guess, a good way to look at decision making and forecasting in one view. Okay, because you don't always want to spend a lot of time to figure out the best forecasting model and then take decisions. You want to forecast while making good decisions. You don't want to lose revenue by testing out 100 different things and lose customers and so on, right? So there's that issue as well. So and I also already said the three techniques. So let me spend okay 2 to 3 minutes on each of this, because you already know some of this. Okay, so how many of you have heard of the ImageNet dataset? Oh, okay, few people. So let me just recap what the gist of the whole thing is. It's some famous thing, and a lot of people have kind of commented on it on blog posts and news and so on. So ImageNet is this huge data set. Previously, we didn't have such a huge data set from 2010 or something, which has about 14 million images. And the images have been categorized. So in the sense, which category does each image belong to? And there are 22,000 categories in that data set. Okay, it's a huge data set. And then, so they started having these ImageNet large-scale visual recognition challenge, okay, which had several, I guess, perception tasks. One of them is classification. Other tasks would be localization and so on. Some other tasks, okay. And in fact, in the classification task, which is called, I guess, task one, they were, subset the data, only 1,000 categories, only 1.5 million images. Okay, and this is still a lot. Okay, you can't really work with this type of data set on your laptop, for example. You really need at least a workstation or more. And then your task was given. You've been given, and this is split into test and train, the usual thing. And you've been given. So given the training data, you learn a classifier, and it should do 1,000 class classification. Okay, 1,000 class classification, and then you're evaluated in terms of a held out data set where you given a new image, you classify it as A or B or C. So what are these 1,000 classes? These are like cat versus dog versus cat breeds, dog breeds, or all sorts of automobiles and so on. Okay, and in fact, the classification task has a slight twist. Typically, you would think of some sort of a loss, which is like the moment you misclassify, you're penalized. Okay, here the classifier is evaluated in terms of whatever it predicts as the class. Is it in the top? Sorry, it should predict 5 things in the sense of if you it's a 1,000 class classification, so there's going to be a prediction that this is most likely a cat, and then next prediction could be if it's not a cat, it's a dog, and so on. So they look at the top 5 predictions, and then as long as one of them is correct, you're fine. So it's slightly different objective. Uh, and and then so given a task, so before 2012, most of the work was based on SVMs, actually, things that we learned in the previous course. So a lot of feature engineering, and then ultimately the last step would be given features, use support vector machines. And then in 2012, one of the labs produced a deep learning based architecture. It's called lec01a, so which showed absolute improvement of 10%. Okay, absolute improvement of 10%. That was a big leap. And since then, I think so. This is only the 2014. I think the challenge itself probably is discontinued, but you got all the way to 93%. Okay, so human accuracy itself is I guess 93, 94%. So you're already pretty close to human accuracy. Okay. So that's the I guess claim to fame, one of the claims to fame for deep learning. And now you see a lot of other things in blog posts, and we'll also see some of these applications. Okay, recent applications include generative adversarial networks used to generate synthetic, faces, new faces, or things like that. So we can do. So we'll see that in one of the lectures. Okay. Um, okay. So let's skip this. Okay, second is graphical models. So graphical models actually historically before like let's say in 2010 to do some image classification, so some image tasks like image segmentation. For example, here's an image segmentation problem where given an image you wanna segment it into road and not road. Okay, so that means you tag every pixel here as a part of the road or not part of the road. Okay, so you would do image segmentation using actually graphical models. So so that's one example of where graphical model can be used. Some of you, so even so, okay, in terms of audio, for example, these days you have deep learning based audio products like whatever Alexa and so on. So let's say before 2010, people were using what are called hidden Markov models. So some of you who are coming from whatever signal processing background might have heard of hidden Markov models. So these were used in speech to text engines, basically like voice recognition and getting the text output. Okay, so they are examples of graphical models, and then there are other things like image denoising and so on. So there were a lot of applications where graphical models were used. These days, deep learning based methods, because you have lots of data, can kind of compete with them or do better. But then but the big useful thing about them is there's a very nice way to infuse prior knowledge, okay, into the task that you're doing. Um, okay, so not so much about graphical models. Okay. Um, yeah, let me give you this example because this is, I guess, more interesting. So, how many of you have heard of topic modeling, where you've been given a bunch of random documents, not random, but it's a corpus to, maybe it could be SEC filings or, reviews, Yelp reviews or IMDb dataset or something like that. And then you want to figure out what are the topics appearing in those articles or documents. So a popular topic modeling technique is latent digital allocation, about 20 years old now, and it basically is essentially a graphical model. And a graphical model essentially looks like this: a bunch of nodes, okay, and a graph-looking object. And it's a model in the sense that the nodes represent random variables, some of which are observed. In our case, the documents are observed, and given the observed documents, we want to kind of infer what topics they belong to. Okay, that's the inference problem. Okay, so this is just a textual description of this particular graphical model saying how were the random variables generated. Let's not worry too much about this right now, but it's a way to say how did we get the data, and given the data, how infer things about the data, like topics, for example. Okay, so so if you want to do topic modeling and more complex things, then this is a good tool to know. Okay, so this is a rough differentiation between graphical models and neural networks. Actually, you can even do probabilistic things on neural networks. So I would say graphical models are more probabilistic in nature, from thinking in terms of joint distribution and random variables. In deep neural networks, you typically don't think of random variables, and sometimes you do. Okay, Mostly you're trying to capture dependencies between these random variables, like the columns of your tabular data. Whereas here, since we are looking at unstructured data, looking at mostly just input output. Like as long as we can have a good function approximator or function which can go from an input to an output, like an image to its label, cat and dog, it's good enough. Graphical models are low capacity in the sense that they have, I guess, in terms of like they're more biased. Okay, because we infuse prior knowledge. Okay, so think of it this way, right? Think of linear model as the most biased prediction model, and then k nearest neighbor is like least biased. Let's say, not really true, but so graphical models would be on towards the linear model side, because we are, when we talk about relationship between random variables, we are imposing a lot of prior knowledge. Okay, so if one random variable is related to another random variable, that's some information right there. Okay, whereas deep neural networks, they also have some bias in terms of some type of structure that they do assume about, for example, images, like translation invariance. Whether the cat is present at the top right or the bottom right, bottom corner, it doesn't matter. Where the object, in this case, a cat, is present. Okay, so they do capture something, but they are high capacity in the sense they can capture very complex relationships between inputs and outputs. Okay, and and as I said, domain knowledge and prior knowledge is easy to capture in graphical models. In deep neural networks, it's relatively a little bit hard, I think. So it's just a rough distinction between these two. Okay. Uh, okay. So let me spend another 2 minutes. So I talked about deep learning. I talked about graphical models. Very quick teasers. Online and reinforcement learning, as I said, is about having a forecasting model, given the forecasting model, taking some decisions, and then getting some feedback on how good the decisions were, and then updating your forecasting model, again take decisions, and so on. Okay, so that's roughly a way to think about it. Here's an example where there's a page, I think msn.com, something like it's just a page where there are a bunch of different articles, so people can click on different articles, read about this. So the problem here is that users, basically, you will have some user profile, you will have the demographic features of the user. For example, what did they do with the web page before, and you also have the page features, which is different articles have different features, like, for example, the topic that they belong to, or how interesting the topic is, sorry, how interesting the article is, and so on. Okay, some features about the articles. Now, given this information, you can always solve a supervised learning problem, forecasting model, which will rank order these articles. Okay, about with respect to how relevant they are, that the person is going to click on them. That's just a prediction model, right? Given the user feature, given the features of the articles, you just want to figure out, make a prediction of which article will get clicked. That's just a classification problem. So you solve the classification problem, but you actually show the rank list to the user, and you actually log what did they do. Okay, and what they do again goes back into your data set, and again you update your model. Again, if they did something else, then you remember that information, and so you kind of improve your model. Okay, that's a very simple explanation, and there are some nuances that we'll get to later. Okay, and in fact, I guess the second motivating example is uh, how many of you have heard of AlphaGo uh, from some time ago? Actually, the first version is from 3 years ago. So since then, there have been several generations of AlphaGo, Alpha Zero, and AlphaGo Zero, and so on. So this is an example of, again, a reinforcement learning system, okay, which learned how to best take decisions by learning. So there's a learning aspect to it, which is it has to learn the nuances of the game, how to play, and so on. Eventually, figuring out good strategies. Okay, what decisions to take given the situation of the game. So the situation of the game, which is the board state in the game of Go. By the way, game of Go is just a board game like this. So this is the picture where the two players, one player puts white stones, and the other player puts black stones. The objective is to capture much of the area in this board on this board. Okay, it's a 19 cross 19 grid, and for example, if you completely circumscribe, I guess, the black, a particular region, then you get that region. For example, there are different rules like that. Okay, so an RL system was trained to play against, I guess at that time, top ranked player from Korea, heavily televised, and the system beat the player 4:1. Okay, in a five game situation. So that's one of the main claims, and there's another claim which is playing video games. Okay, not just these 2D games these days. People are developing RL systems or reinforcement learning systems, which learn how to the rules, the dynamics of the game world, and take optimal actions, which is to get more points. Okay, so games like Doom or Defense of the Ancients or StarCraft or any of these multiplayer games or first-person shooters and all that. Okay, so this also happened pretty recently. It's 2014 maybe. So these are some teasers of what where people have gone. Okay, these are the frontiers of how to use RL techniques or deep learning techniques or graphical models. But there are a lot of industrial use cases as well. So at least Google says that it has used some of the learnings from doing this for cooling data centers in a very efficient way. Okay, data centers consume a lot of energy, so even kind of saving 1% or 2% energy is like a big deal. Okay, um, so finally, caveat. As I said, again, circling back to that $1 million slide that I said, most of the techniques are just probably you can replace them by first trying out an SVM model or a random forest model first. Okay, for example, if you're just doing class supervised learning setting, because you really want to ask what is the bang per buck. So if you increase classification accuracy by 20%, maybe it really doesn't translate to much in terms of revenue. But then you need somebody who now doesn't just know logic regression, but also needs to know deep learning. Maybe you want, instead of a bachelor's degree holder, you want a PhD degree holder or something. So there is gonna be costs for different tasks. So especially what I call what people call technical debt. So it's something very important, and so as I said, whatever performance increase you see in these tasks ultimately have to be tied down to the business goal. Okay, that's kind of the key. So any questions so far? I did a very quick teasers on uh, deep learning, graphical models, and reinforcement learning. Am I too fast? No. Too slow? It's fine. Is it too slow? Okay. So let's. So what we'll do. So what we'll do is two chunks of modular things. First is just quick recap of classification. So this part is going to be a little bit of recap. So if you don't agree with what I'm saying, then or if I since there'll be a slight change in notation, so ask questions. Okay, compared to, for example, some of you took my class previously. And the second part will be just about back propagation. Okay, it's just another name for chain rule. So we'll look at backprop. Okay, so those are the two things we'll do next. So let's jump into classification. So as I was saying at the beginning of this lecture, classification essentially has four important ingredients. So first of all, classification is a supervised learning task. So you have data which has both features and labels or targets. So there are four components: data, model as a model class, the metric loss function, and then how do you get the best model for this metric? What's the technique? And that's optimization. Okay, so those are the four components. At least in my lectures before, I did not focus so much on optimization at all. Okay, mostly it was about models and what the loss function is. Okay, um, so here's what a classifier has to do. It's supposed to classify, right? Given an example, you just need to figure out what's the right label. Okay, and here's one example of how to think about data, especially in the unstructured situation. So let's think about image. Okay, uh, so so image is a data which just doesn't look like a tabular format, right? It's not a feature vector. Okay, so what is an image? So image in terms of for our algorithm or for our model is just going to be a a collection of numbers, and each number, let's say, is between 0 to 255. So why that? Why not between 0 to 1? That's not a big deal. Let's say 0 to 1 or 0 to 255, doesn't matter. It's going to be a three-dimensional array. Okay, or a three-dimensional array is essentially a tensor. Okay, a two-dimensional array is a matrix. A three-dimensional array is a tensor, three or four or five. Okay, it's just a collection of numbers arranged in a rectangular or cuboid format. Okay, how many of you did not agree? Did not? understand this what I said? Okay, so I think I can write. Yeah. So this is nothing but so you know matrix, right? So that's a 10 cross 3 matrix. So 10 rows and 3 columns, right? Sorry, I drew 4 columns, but anyway, so that's a two-dimensional array. Okay, that's an array is just a collection of numbers, collection of things. So this is a two-dimensional array, and a tensor is nothing but a something which has a depth in it. Okay, so it's the collection of numbers. As if I have matrices I stack next to each other. I mean behind each other, and then I have a like something which has depth. Okay, but it is still a collection of numbers packaged in a nice cuboidal format. Okay.
And
That's what an image is what I'm
0 to
claiming.
255 is which is one of those three dimensions.
No, 0 to 55 is the entry value in the cell. So in the matrix, yeah, it's just the numbers in the cells of the matrix, or in this case, a tensor. It can be any number. 0 to 55 was just something to do with discretization. Okay, so I think like if you do anything to do with colors on a computer, and I think in some color scheme, it's basically 255 represents white and 0 represents black. Okay, in grayscale images, 0 represents black and 255 represents white. So when I said a three-dimensional array, I was talking about what are called RGB images. So there's a red channel, there's a blue channel, and there's a green channel. So it's like three grayscale images, but each one, the first grayscale image is talking about how intense the red color is. The second grayscale channel is talking about how intense the blue color is. The third channel is talking about how intense the green color is. Okay, so the intensity is just, I guess, one of these numbers. Okay. It could be 127, 0, 10, to 200, whatever. Okay. So the three-dimensional array was typically an image will have three channels, and together, when they're stacked on top of each other, you look at it, it's a color photograph. Okay, where each channel is only picking one primary color.
And it's representing three-dimensional space in real
No,
life.
it's just representing a picture. No, it's just representing an image. Like that's it. Is that not clear? So like uh, yeah, so like, this is an image, right? I guess I can't. So this is an image, right? I mean, forget about the text in the front. So this image is essentially an RGB image where it's essentially can be, if you load it into Python as a data, as an observation, like let's say it's an observation with its label being a road or something. Okay, then it's just a three. It'll have three channels if you load, as in like just like you read CSVs. So pandas or read CSV or something. So you can read this image into Python as a object, and you can store it as like a three-dimensional array. So three matrices. Okay. Sorry.
Red, green, blue. Is that it?
Yeah. Each matrix is like a red, green, blue, and in the red, how many? What is the intensity of that color at each pixel? I mean, the three dimensions was not for the three colors, but like there are three dimensions. One, the width, the height, and then there's a depth. Okay, those are the three dimensions. Depth is three. It happens to be three as well. Okay, three colors. I mean, you can also have images which have depth information as well. These are called RGBD images. Like lidar, for example, will give you some depth information, like how far is that table, how far is that wall, and so on. So that will be the fourth channel. Okay, so those images are different. Those are typically used, I guess, more for autonomous driving and so on, security maybe. Anyway, typical images that you get clicked from your iPhone or things, they're going to be three channels. Uh,
Would there be a way to, I guess, flatten that into like a 2D representation, or is that just not a thing?
no, that is sorry. The 2D representation is the image. Like if you want to visualize, so this is the image, right? That's the 2D representation. You flatten the three matrices. I mean, it's not really flattening, but you're looking at the three layers together, so that's why you're able to see the colorful picture. But if you saw only one layer, it will only be about red, it will only be about green, it will only be about blue. So you'll not see differentiation. It's like a grayscale image versus a color image. Um, anyway, and just some nuances. I mean, I just wanted to give an example of unstructured data, which is this. And unstructured, I just say because it's a collection of numbers which are like raw, right? I mean, it's because the image sensor captured, the photons or whatever. In that way, we have a certain height, a certain width, and certain depth. Okay. But that's the image. So there's no name, there's no feature name yet, right? There's no features. So, and of course, an image gets influenced by 100 different things: location of the camera, location of light, occlusions. All these influence the same object that you're seeing in the image. Okay, so although it's the same thing, the road, it can get influenced by a lot of other things. So in terms of notation, we're going to use the following notation. So xi, yi, little xi, little yi, which means the ith image, let's say, for example, in vision, ith image and the ith label. Okay. So, and then there are, let's say, capital N number of images. And and that's it. That's the notation for the data, actually. Pretty simple. And I just wanted to point it out that given this xi, so you could have a feature extractor, let's say um, HOG of xi will give you a bunch of features. Okay, maybe it'll give you 3 features, maybe it'll give you 10 features. So these are, so when I say feature extractors, I'm just saying that before deep learning, you would just you get the image. Okay, maybe it's a photograph, it's a face of somebody. Then you'd figure out where's the eye. Okay, and that would be an extraction. Oh, there is an eye first of all, and the eye is over here. Those are like hand engineered feature extractions. Okay, hand engineered feature creation process. Okay. And there are some names, some popular names for how certain types of features which people have developed over a few decades. We'll not really go into the details of what these feature extractors are because we'll directly use some deep learning based techniques which extract which don't need these notions. Okay. Uh,
Professor.
yeah.
So XI in the machine learning algorithms is basically all the features. What will be the XI in deep learning? So if it is going to be a tensor, the data matrix, if it is a
This
matrix,
xi was let's say yeah, I mean belongs to R. Okay, R is just reals. Okay, let's say you have an image which is 256 cross 256 cross 3. Okay, that's the dimensionality of xi. Yeah, if it's an image. If it's a 256 cross 256 pixels, really small image. I mean, if you actually get it from an iPhone, it'll be a 1 megapixel cross 1 megapixels, basically 1,000 cross 1,000 pixel image. Okay, with 3 channels. Okay. So xi for us would be something like that. I mean, this is just I guess a shorthand notation to say that xi is a tensor, is a 3 dimensional array. Okay. Little xi is a 3 dimensional array. Now, at least in my class, I use capital Xj to represent the jth feature. Okay, like this column corresponds to like pressure. This column corresponds to temperature. I use capital X. Okay, that's like a placeholder generic name for the feature. Little xi is the ith observation. It's a row of that matrix. Okay, capital X I would be the column name for the column. Okay. And okay, so that's our data. That was an example of image data. Now let's talk about models. Okay, we have seen a lot of models before. We've seen logistic regression. We've seen random forest. We've seen SVM. We've seen KNN. So there are a lot of models. Many models come with parameters. Actually, most models come with parameters that you have to tune. Okay, but some models which have very few number of parameters or parameters can scale as a function of the data, they are typically called non-parametric models. Okay. But for us, we'll not have any such distinction. We'll just focus on, since we're focusing on neural networks, we'll have a bunch of parameters for neural networks. So neural networks are also a parametric family of models. Okay, and we'll typically people distinguish between parameters and hyperparameters in the sense that parameters are like, for example, think of SVM, right, or even ridge regression. Both have essentially the same thing. Linear models, right? You would think of the beta coefficient in ridge regression to be the parameter, and the ridge. Okay, let me write it. So let's say you're doing ridge regression. Sum over I is equal to 1 to n. Okay, of xi transpose beta minus yi square plus something like this, right? This is what the ridge regression objective function looks like. You try to minimize over that linear model beta, right? Remember, this is just least square split sum regularizer, which is the ridge regularizer. So you would call beta parameter and lambda hyperparameter, because you would probably kind of optimize for the hyperparameter using cross validation, and you would optimize for the regular parameter using just optimization or training, or I guess in our case it'll just be back propagation. Okay, so it's just a nomenclature difference between these two. I mean, both together influence what ultimately you get as a model. Okay, so okay, hyperparameters don't feature, I guess, once you've already trained the model. So once you already have the beta, then you don't need the lambda, for example. Okay, so that's models. Uh, so this is a slide where there's a slight change of notation from my previous course. For those who have not seen that course, that's fine. So I'm gonna let's pick a particular parametric model. Okay, so f of x comma w comma b. I'm using two parameters now. W and b are going to be parameters, and x is going to be the input. Think of x as a feature vector, or in our case the image. Okay, whatever it is. W and b are going to act on it. Okay, those are the parameters of this function, explicitly written as second and third argument, and f will output something. Okay, it could be the class label, or something like that. In this case, so in this example, let's say x is d-dimensional. Okay, let's say we had an image which had like 256 cos 3 bunch of numbers, right? I could always like stretch them out into one vector, which would be a huge long vector, right? That will be my d-dimensional vector. Stretching out a matrix is just like if let's say you have a 3x3 matrix, then you put the second column below it, third column below it, you get a long vector, right? That's all I mean. Okay, so vectorizing means that, not very critical. So you have an x, okay, which is some dimension d, and then w. Okay, here is an example model. Let's say w is a parameter which is p times d dimensional. Okay, so p times d dimensional, and let b also be p times one dimensional. Specifically, this is, let's say, f of x comma w comma b is this. Okay, so here I guess these three choices were just to ensure that the dimensionality is matched. Okay, w is a matrix, okay, which is p cross d dimensions. X is a vector which is d dimensions. So the matrix times the vector will give me a p dimensional vector. I need to add to that another p dimensional vector. That gives me a p dimensional vector. Okay, that's what the output of f is. Okay, so this is a parametric model. It's producing a p dimensional vector of what we'll call scores. Okay, so linear model will produce some number, right? Linear model is just a linear transformation of the input. That's what's happening here. This is a linear transformation of the input. And once you transform it, think of outputting some real numbers. These are called scores, which ultimately get transformed to probabilities in classification, or in regression you just leave it as it is. Okay, so yeah, so important thing to note from this slide is, I guess, we'll call the output of this any like, let's say there's a model with some input and some parameters. It'll output what are called scores. Okay, that's the model. And is this point clear, or is there some confusion?
So over here, W basically equal to the image size, right?
Yeah, I mean, so let's not worry about image itself. So since I vectorize the image, for me it's as good as saying I'm on the structured data set where I have like a 10-dimensional data observation, or like a 20-dimensional feature vector.
So X is basically the image, all the vectors put one behind the other, right?
So originally X was the image. I said vectorize the image, or if you get some features from the image.
So vectorizing the image is basically
Like just
converting it into
a vector.
a matrix.
Into a vector. Vectorization means just making it a vector. So it was remember it was a 3-dimensional tensor, right? Had some depth, it was a bunch of matrices stacked. So what you can do is, just rearrange the numbers so that they are one below the other. That's essentially what a vector is, right?
So for image data, is it going to be 768 into 1
Yeah. Actually, you guys have done this, right? So some of you, now I remember. So I think in the first assignment of 575, at least in my class, you worked with MNIST data. MNIST. Remember this images of digits, and then you are trying to classify it as uh, 3 or 9 or something through two digits. So there it was a 28 cross 28 cross 1. Okay, it was a grayscale image. I mean, it was a black and white image. Okay, it's either that was the image, and so 28 cross 28 leads to that 784 or something. That was the length of the feature vector. So that's x here. Okay. So we had an image, we just straightened it, and now it's like lost all its image specific information pretty much. Okay, but that's just for example purposes. Um, yeah. So
What is P over here now? P into
yeah, P. Good question. So what is P? So if I have a 2-class classification problem, P is going to be 2, and if I have a 10-class classification problem, P is going to be 10. Okay. It's a very important question. So where is this? In the previous slide, here, this beta is actually like the W and B parameters, okay? Where beta is just 1, P is 1 here. Okay? P is 1. Um, yeah, if I had written beta transpose X, then beta transpose is a W. Okay? Beta transpose is a row vector. So its P is 1, and the number of columns is the same as the number of, is D dimension, just like X. Any confusion here? I see some questioning, some people. It's fine. It's a small class, so we can take some time. Unless some people are bored. Who's bored? Okay. I think it's important to ground the notation. So, uh, so all I'm saying is that f of x function, let me not even write, is just equal to wx plus b. Okay. So remember, if I was doing regression, and let's say my output or independent variable was just one dimensional, then this w is not really a matrix. It has to be like one cross d, and this is d cross one, and this is one cross one. It's basically like, let's say even d is equal to one, then it's just you know. Uh, it's like mx plus c. Okay, some model where m is a slope, bunch of data points. This is x, and this is f of x. Okay. If you are doing regression, our target variable is one dimensional, and your feature itself is one dimensional, then it's essentially like a y is equal to mx plus c type of equation. Okay. Y is equal to mx plus c. I mean, f of x is nothing but y. So we just use slightly different notation. So why am I not using? I mean, here we could have just used instead of w plus b, we could have just used beta transpose. Okay, then it would have been just equal to beta transpose. Let me not use beta transpose x plus, let's say, beta naught, if you do not have an intercept. So that would be the linear model. That's an example of linear model. We just changed the output dimension a little bit. That's why I added p there. So now you're not predicting just one number, you're predicting 3 numbers or 10 numbers. Okay. And why would you want to predict 3 numbers or 10 numbers? Because if you have 10 classes, then those 10 numbers can represent how much you think that it's of one of the classes. Okay. So if let's say you're predicting 10 numbers, and let's say the first number corresponds to how much you think it is of the class cat, but the second number thinks how much it is of class dog. And if first number is really large, your guess is that maybe it's actually a cat. Okay, that's the intuition behind. So this is just a simple linear model. So there's really nothing going on here. It's just linearly combining the inputs to say, oh, how much is it a cat? How much is it a dog? Okay, I mean. Um, okay, so that's model, and we'll see. Actually, we'll put them all together pretty soon. And so that's what I said. So I was saying, if you're going to make P predictions or P predictions, and if you want to do classification with it, then you can think of these P numbers as, strength of what I think is, whether it's the first class, the second class, or the third class, and so on. Okay. And then how would you make a single prediction? You just pick one of the coordinates which has the highest score, and that would be my prediction. Okay. That's represented by this argmax operation. So argmax just means, okay, I have 10 numbers. Tell me the index of that coordinate which has the highest number. That's the argument. So maximum of those numbers is not what I want. Where is that maximum number? That index is what I want. That will be my class, like class index, like third class or the fourth class or the fifth class is my prediction. Okay. So that's what this means. So, and then let's say if that is my prediction, then you want to say how good is my prediction, and that you evaluate by a suitable loss function. Okay. So loss functions you've already seen, like in the regression case, I already put a square loss, beta transpose x minus y the whole square. So here the loss would be, let me show it in the next slide. So there'll be some loss function, and then the fourth component, optimization, will optimize for the best model that minimizes or maximizes, minimizes its loss function actually. Okay, those are the remaining two components, and so to define the loss function, let's call the jth coordinate of my linear model, or for simplicity, let's think of the linear model as Sj. Okay, so what do I mean by that? Let's go back to that this thing. So all I'm saying is, you have Wx plus b. W is p cross d dimension. This is d cross 1, and this is p cross 1. Okay. Now this I'm calling it as S1, Sj, Sp. The p score of how much I think it's a cat, how much I think it's a dog, and so on. This is a linear transformation. This part is clear, right? Matrix vector multiplication plus some vector addition. Okay. Now these are scores. Okay. And I don't like the slide animation, but okay. So 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 let's say loss is I'm calling loss as L data. Okay. And this loss is going to be a sum of n terms. Okay, just like remember linear regression, we had a loss function, square loss, which is a sum of n terms, where n is the number of training observations. For each observation, there's going to be a loss, which I'm calling it as Li. Okay, for each observation, whether for that observation I made the best prediction or the classification or not, is Li. Okay, and here are two losses. So let's just focus on which one? I guess let's go linearly. So let's look at logistic loss. Okay, so pay attention to this. Logistic loss is also called cross entropy loss or the softmax loss. So actually, when you did logistic regression previously, there was a loss function we used, and that loss function is what is called cross entropy loss or softmax loss. Okay, two new names for the same thing. Okay, and how does the loss function look like? The loss function is for the ith observation is going to be for this feature xi. Okay, I was supposed to predict yi. Okay, but I would have a score for the yi. Okay, yi could be, let's say, class 3. There will be a score for class 3, and so let's say j is 3. Okay, then there will be then given the scores, given all my scores, my probability of predicting class 3 would be the e to the power the score for the third guy divided by sum of e to the power scores of everybody else. Sorry, not everybody else, everybody. Okay, this is just a way to bring the scores. Okay, scores can be any numbers. Okay, anything between ranging from 100 minus 100, whatever number. Okay, what we are doing is first we're saying, okay, for this observation, let's we'll have all these scores. That's what f will already give me given that observation, right? It will already produce all these scores. Let me normalize, as in change the scores to some new numbers, which I'm calling as probabilities here. Okay, it's just the probability of being in class J given a feature. Okay, that's the scores. So e to the power the score for the jth guy divided by e to the power score of everybody. Okay? If there are 10 classes, then this will have 10 terms in the denominator, and this is the probability of predicting class J. Okay? But we care about probability of predicting the true class. Okay? For xi, there was a yi corresponding to it. So tell me how much score, how much probability did you assign to the true guy? Okay, the true class, true label for that observation. Okay, and whatever the probability is, the negative log of that is called the loss. Okay, the lower this number,
Negative loss.
the lower this number, I think you have assigned lower probability here. Okay, so li being sorry, apologize. So lower the number means you have assigned a high probability here. Okay, which means that for xi, yi was a true guy, and this number you made it high. Okay, which is the right thing to do because yi is a true class for xi. Okay, so if you try to minimize this loss, the only way to minimize is to increase this number. Okay, is that clear?
Did you say that last part again?
So all I'm saying is, okay, so remember, if you want a good model, the model should have a low loss on the ith example, right? If it has to have a low value here, the only way to get it is to increase the value of this probability. Okay. See, because see, probabilities are numbers between 0 to 1. Okay. So already log of some number between 0 to 1 is already negative. Okay. So so that negative and negative, just ignore this negative part.
They cancel out.
Yeah, they cancel out. So all I'm saying is, if this probability, if this p term is low, then the log of that p term is going to be some number which is like huge. Okay, ignore the negative part. Okay. So let me actually give you a specific example. All I'm saying is, if p of the so let's say y is equal to yi given x is equal to xi. Let's say this is equal to either let's say 1 by 10 or 9 by 10. Okay, then negative log of 1 by 10 is what? 10. Okay, right? Okay, so negative log of 9 by 10 is some number. So let's say, let me call it 9.99 for example, so that it's easy to illustrate. 9.99. My god, my handwriting is so bad.
So is the big idea, the bigger the input, the larger, sorry, the smaller the input, the larger the output? Like numbers really close to 0 are going to have huge results when they come out.
No, I'm just saying that I'm just showing you that why this loss function makes sense. Okay, you've always seen this loss function in a different way of motivating in my previous class. Now I'm motivating in a slightly different way. Okay, you've already seen multi-class. Sorry, you already seen logistic regression before. Okay, where it was about the log probability ratios being constant or being linear. Okay, that was the so remember, I don't know, some of you remember that we looked at linear discriminant analysis where the log probability ratios were supposed to be linear, and we could get that if we assume normal distribution of the features, and yeah, normal distribution of the features was NF. And then the logistic regression was where we did not have to assume normality. We directly assumed that the log probability ratios were linear, and that gave rise to, under that assumption, we got some loss function. Okay, we probably didn't focus too much on that. That loss function is the same as what we're talking about here. Now, this I just wanted to say that if it's 9.99 by 10, it's almost close to 1. Okay, so log of 1 is 0. Okay, all I'm saying is that if you have this number high, instead of close to 0, close to 1, then the loss, which is the little negative log of that number, is going to be close to 0. So high that, low loss, low that, high loss. Okay, and we care about minimizing loss. So we want, for the true label that the observation belongs to, this number needs to be high. Okay, and when will this number be high? When the score for this number, y, I think I should put yj, but the score for, sorry, not yj, the score for this particular example for the true label should be high. Okay, that's all the intuition. I should now stop switching this because it's too much animation. So the next one. So is the logistic loss clear? This is it. This is the logistic loss. Okay. So here's a more, I guess, if you have n observations, then you would have sum over I is equal to 1 to uh, okay, let me actually, so for the ith observation, I just wrote that the loss function is like this, right? So let me write it in a slightly different way. J is equal to 1 to P, okay? Okay, and indicator of, sorry, indicator of y is equal to yj. Uh, sorry. Okay, this is not correct. Let me just write it in a different way here. Okay, so the logical loss is what? Minus log probability of y is equal to yi given x is equal to xi. Okay, it's just saying that, oh, you already trained the model. So in fact, this is what the model is. So p hat, I'm putting a hat because p hat was actually, this was equal to e to the power s yi divided by sum over e to the power all the scores. Okay, k is equal to 1 to p. If I have p scores, just compute this number. Whichever was the true label, just e to the power that guy score. That's the numerator. This is nothing but this. Okay, that's my prediction. Okay, that's my prediction of for the true label. Now this was logistic loss. Okay, and all I'm saying is this is equal to sum over j is equal to 1 to p. Okay, of minus. I don't want to write indicator. Let me just write um, minus yi times p hat of um, yeah, y is equal to j given x is equal to xi. So what I'm trying to say is that, let's say I predict, given the xi, that's the probability that it belongs to class 1, class 2, class 3, class 4, class 10. Okay, so I have these numbers, right? P hats. So there's a log in the front. Okay, I have these 10 probabilities, right? I can compute those probabilities. All I'm saying is this loss function is just saying that only pick one of those 10 terms, the term corresponding to the true label, and that's my loss. That's all. Okay. And why did I want to write this term? This is actually very similar to entropy. Okay. So entropy is a function which looks like this: sum over um, qi minus qi log qi. Okay. This is called entropy. Okay. Let's say, let me just put j here. This is called entropy. Okay, if you have a random variable with p values that it can take, then there's a probability that it will take one first value, second value, third value, and so on. Let's these values be q's. Okay, then the entropy of that random variable is defined by this. Okay, now if you just pattern match with the expression above, okay, two things changed. Instead of qj, I wrote some probability of y is equal to yj. Okay, that's fine. That's my estimated probability that it's in that class. Okay. Now instead of this qj, there is some yi. So what is yi? Is just in my ith example, whether it's class, what class it is. So actually this yi, um, let's say it's the class is cat. Okay, cat is the first coordinate. So then yi should be something like this. Okay. Okay, yi is something like this. Okay. So all I'm saying is, so you can see that, right? Because if this is the case, then there'll be p minus 1 terms which will be not there, and the term which actually corresponds to the class will be present. That's what this is, original loss function, right? I just added a summation. So of course there has to be p minus 1 terms which somehow get rid of. So the yi is like a bunch of zeros and 1 at that location, which actually is the class of that. Now, if you look at the definition of entropy, just this is the definition of entropy. This term looks like probability. That's this probability. This term, instead of plugging in the same probability, we plugged in the true bytes, the true labels. Okay. So this is like a very degenerate probability distribution. Okay, where it's like zero mass on all other values and mass of one on one of the values. Okay. So that's why this term is called cross entropy. So this is entropy because it's only for a single random variable. Cross entropy is like two different distributions. Okay? One is this my predicted distribution, predicted score, and this one is the actually true label, which is like this degenerate distribution. Okay. We'll probably intuit more about this.
Yeah, the output of the network would be probabilities, right? This would come after.
There's no network so far, so
like whatever, like if you are doing image recognition, then
yeah.
it will give us probability for each class.
Yeah, that's what we're doing, right? So we are doing classification. We're getting these probabilities.
But in the cross entropy function,
Yeah.
if we directly put this.
This is the cross entropy function. I just wrote it as an additional summation here, just to show that to resemble the entropy form. But this is a cross entropy function.
But eventually we'll calculate the cross entropy function.
Which is this?
The summation one. But if we have
I mean, I just added frivolous summation because the other terms are zero, gonna be zero. To just kind of replicate how entropy function looks like. Entropy has a summation. Okay, if you just look at Wikipedia entropy, it'll be a sum over p terms if there are random variables taking p values. Here they did not look like a sum, so I just tried to help you intuit how is it related to entropy, so that at least you understand the name cross entropy. Softmax is actually just because this type of a transformation from scores to exponentiated scores and normalization is just called softmax operation. Okay, and if there are only two scores, it looks like the sigmoid function. Okay, something like an S function. So we'll kind of revisit these things again and pretty soon again. So
are we going to minimize the loss for each observation, or is it going to be?
No, we care about model the parameters, in this case W and B, such that it minimizes the whole data loss.
So it is for
That's supervised learning. Yeah, I'm just recapping supervised learning here. Yeah. So, so let me skip SVM loss, but I don't want to confuse you guys more. So, okay, so loss function, there's another part, which is the loss function due to the data, the labels not corresponding to the true labels. Okay, and now you have regularization as well. So that's the second part of defining this loss function metric. Regularization is motivated by multiple things. One is maybe like think of ridge regression, right? We added the ridge penalty or the regularizer so that we prefer models which have low coefficient values, for example, or we prefer models which have maybe there's no unique model there. Then the ridge regularizer will regularize towards at least a good linear model. Okay, and you can also control overfitting. So ultimately, what is a regularizer? It's like L data, which we just saw earlier. It's a sum of n terms plus some constant times a function which only depends on the parameters. Okay, remember regularizer previously was just the 2 norm of the coefficients. Here it will be something similar. 2 norms of W is a matrix, so instead of 2 norm, you can actually do 2 norm of a matrix as well. Okay, and here are some examples. So typically, what happens is we don't really penalize the intercept. So the B is like an intercept. It's not really interacting with the data at all. So we penalize the W. Okay, and one example of 2 norm on the matrix is the sum of the squares of the entries of the matrix. Okay, it's not really called 2 norm actually. It's called the Frobenius norm, but for a matrix, but doesn't matter. So it's just the sum of the squares of the entries of the matrix, entries of the parameter. Sorry, sum of the squares of the parameter values. Okay, and 1 norm was the absolute values. Just remember from your ridge regression and lasso example, those are these two. And okay, elastic net doesn't matter. So there are some other ways to regularize as well, not just explicitly having these norm preferences. Okay, in the objective function, there's also something called dropout. Okay, dropout is just a name for now. It's a mystery for now, but it's a way to regularize neural networks. Okay, and you can also regularize other ensembling methods and so on. We'll see that's another way to regularize. Okay, so that constitutes our loss function and our preference over models. Okay. Now, how do we optimize? So this is what the block diagram picture of the whole situation looks like. So we have some parameters which characterize our model. Okay, those parameters influence our regularization value. Okay, maybe there are some parameter values or ranges that we don't care about or we strongly prefer, and w comma b also influence for each example the scores. Okay, the scores are computed using the parameters, and then we just want to ensure that these scores are as close to the true label as possible in terms of, for example, we saw the logistic loss or the cross entropy loss. Okay, that's this L function. So the overall L function has the data part and the usual regularization part. Okay, with some coefficient gamma balancing those two. Okay, so here W and B are the parameters and gamma is the hyperparameter. Okay. Just like in ridge regression, instead of W comma B, I just had a beta and gamma was a parameter. Is that clear? So instead of, so you might be getting confused with the W comma B. Just think of some parameter theta. Okay, if it's a linear function, that's beta. If it's a complicated messy function, it could be something else. Some parameter theta influences my data side loss as well as the regularization aspect, and then we want to pick the best parameter such that that minimizes loss, overall loss. Okay.
So what is R?
R is the regularization function. So we saw R here, right? R was this function. So okay, uh, so what do we do in optimization? And there's actually a lot of techniques in optimization to find the best parameter. Okay, but we'll kind of concern ourselves with some popular techniques that some of you might have heard of. Essentially, gradient-based methods. Okay, these are called first-order methods because we only use the we not just the function but the function's gradient. Okay, second-order methods use not just the first gradient but the second derivative as well, basically. Okay, so we only focus on first order methods. And what is a gradient? Just to remember, gradient is nothing but a vector of partial derivatives of the function. Okay, so what do I mean by that? Let's say I have a function of two variables. Let me call this function g has of variables x1 and x2. Okay, let me actually put capital X and capital X2. Okay, is equal to, let's say, x1 square plus x2 square. So this is a function in two dimensions, right? It has two arguments and it evaluates to some square of the first argument plus square of the second argument. This is a function. So the gradient of this function, is going to be a vector, which is going to be the derivative of g with respect to x1 and derivative of g with respect to x2. Okay, that's it. That's a gradient. Any questions about this? Partial derivative just means when you take the derivative with respect to x1, other variables are kept fixed. Okay, they are not variables. So if it happens that, for example, the partial derivative of g with respect to x1, you are keeping x2 fixed. So if you take the gradient, it will just be 2x1. Okay, just to recap so that you're not confused. Okay, so this is nothing but 2 times x1 and x2 in this example. Any questions? Confusions? Okay. And you can compute these gradients either numerically or analytically. Actually, and that brings us to our, I guess, second part, which is going to be, we're going to look at backpropagation. Okay, so this is going to be a little bit more cleaner way to compute gradients. Okay, you don't want to always numerically figure out, oh, if this is the function, if I slightly change the one of the arguments and keep the remaining argument fixed, then how much does the function evaluation change, and really compute this ratio? That would be a gradient, but that's very messy. This is the definition of a gradient, by the way, and if you look up Wikipedia, but we'll not do this. Okay, we'll just use the basic facts. Like when I said gradient of g with respect to x1 is 2x1, we just used calculus and chain rule. Okay. I mean, here there's nothing. I mean, we just use the basic fact here, but we'll get to chain rule next slide. Any questions at this point? Okay. So let me spend one more slide on optimization. Actually, we are not going to really think too much about optimization, at least in today and the first few lectures. So what we do in optimization, and this you must remember, even for example, logistic regression, is that you start with some candidate model. Okay, let's call it W0 B0. Evaluate the loss function. Okay, and somehow use the gradient and the current evaluation to go to another candidate model values W1 B1, such that the new loss function is smaller. Hopefully, the new loss function is smaller. Sometimes it may not be, but you take the gradient. So use the gradient information to do this change. Okay, going from the previous old candidate model values to new candidate model values, and then you keep repeating this. Okay, so that's what a gradient descent method would look like, a first order method where you have a current candidate model, you have the loss value with respect to it, find the gradient of the loss function at the current value, and then slightly perturb the current uh, parameter values using the gradient such that you get to a different location, new parameter values which have lower gradient, lower objective value. Okay, so that's what gradient descent does. We'll see in code soon this idea. Okay, and you can also do something called batching. Um, so it's not very critical to understand batching right now. It just means that, let's say I have a billion examples, okay, billion observations. So I can't take the average of these billion, average or the sum of these billion things to define my loss function. Remember, my loss function was sum over n of all the little li's. So instead of taking, I can't take the sum of these billion things. It may waste my time. So what I'll do is I'll take the gradient with respect to only 10 of them or 20 of them. Okay, 20 of my examples. So I'll randomly pick 20 examples. Just find the loss value for those 20 examples, and then take only gradient with respect to those 20 examples. Okay, that 20 examples is called a batch, and that's it. Then you do gradient descent. So remember, and then do gradient updates, and the updates actually just look like this. Okay, so whatever the previous value was, minus some constant times the gradient of the loss with respect to that parameter. Okay, so if the parameter is a matrix, then this gradient also looks like a matrix. Okay, that's just for now a fact. We will see why it is the case. Or if the parameter is a vector, then the gradient of the loss with respect to that vector will be a vector. And so you can do some update like this. Okay, in fact, naively, by just looking at this, if you code this up, it will work for logistic regression, linear regression, and all these models. Okay, and these constants alpha and beta are called learning rates. And we'll revisit these words again and again. Today, I'm just throwing a lot of information to you guys, but we'll revisit them so that subsequently it'll be easier. Uh, and then that was about parameters using gradient descent. One last point about the hyperparameters. Hyperparameters you can tune using the ways that you have seen before, cross validation. Okay, if I need to figure out what is that strength of the regularizer, I try 10 different values, 0.1, 1, 10, 100, 1,000, and then whichever value gives me a good enough model which has good out of cross validation error rate, that's the model I'll pick. Right. So I'll not go through the details of cross validation here. Sometimes it may be too expensive to do cross validation, so you may just do simple validation. So just have one, no cross validation, but just validate some held out data, and you just always train on the train data and always check on the something that you did not use for training. Okay, so you're not really doing cross validation, but you're just validating by every time training on the data set, training data set, and always checking its performance only on the held out data, and never using the held out data for other things except for checking the value. Okay, I mean it's not looping back to improve your model. So any questions so far? I think there was a part I think about softmax and cross entropy was a little bit messy, but we'll revisit that today today and next lecture, because we'll look at logic regression today, and we'll look at feed forward networks next lecture, and both have essentially the same loss function. So we'll keep visiting the loss function again, this particular loss function again and again. So you'll be comfortable in a couple of lectures. Okay. So let's take a 5-minute break, and we'll come back to backpropagation, which is the last topic for today. Okay. And backpropagation is just what is it called? Chain rule, so it should be relatively easy. So any questions you can ask me now. You can come forward.